Hello, my name is Joe Evans from AD Technologies, and in this short video I'm going to talk about the theory of operation for Radiant's Precision Nano Displacement Sensor. I have assembled the microscope, connected to the e-box, and connected the tester, e-box, and the camera from the microscope to a host computer, in this case a laptop I have sitting on top of the tester. I have also assembled a sample holder, sample mount, with the special PC board to hold the TO18 reference capacitors that we supply with the system. So the reference capacitor is located now on the chuck and it's connected by the mini grabbers to the drive and return of the tester, so I can do a hysteresis loop on the sample. And it's got actually a very nice hysteresis loop. I've also mounted a cantilever in the cantilever card and mounted the card inside the light lever stage. At this point, the next step is that I have to take the camera using the translation stages and find the cantilever so that I can align the camera visual area with the cantilever. You can only see the cantilevers because they're so small at very high mag in the zoom, but to find the general area at first, you'll have to back off on the magnification of the camera. And then as you narrow in on the cantilever using the translation stages, you can increase the zoom. And you have an adequate view, a very good view of the cantilever at maximum zoom on the camera. Once the camera has the cantilever centered in its view field, you then can do the thumb screw and rotate the camera until the camera axis, horizontal axis, lines up with the cantilever horizontal axis, and then tighten the thumb screw. This gives you the proper visual reference on the camera view on this host computer screen. Finally, we would lower the cantilever slightly, then move the sample using its translation stages until it's underneath the cantilever in the view of the camera. The final step is to adjust the focus of the camera on the surface of the sample, because we want the cantilever very high, so when you hit it and break it, align the sample where we want using its translation stages. Focus on the sample and then bring the cantilever down using the knurled knob on the stepper motor until it comes into view and then is almost but not quite in focus. By being on focus on the surface with the cantilever slightly out of focus, that means the cantilever will be above the surface of the sample. We now do the final adjustments on the translation stage to put the target area under the cantilever. At this point, we can turn the rest of the operation over to the software. We'll start the automated tip approach. When that happens, the e-box will lower the light stage in steps using the stepper motor, and at each step it'll take the chuck and move it up and scan it, and it'll keep repeating this until the cantilever touches the surface of the sample. At that point, the e-box will see the laser spot on the photosensor move. The laser's here, hits the mirror, bounces off the cantilever or underneath the card, back through the slot to the photosensor. And so this light lever is the means by which it detects that it's in contact. Once it's established contact with the sample, the e-box will hold that cantilever in that spot. Now, if we apply a voltage to the sample surface and we make it move up, it will push the cantilever up, which will cause the laser spot on the photosensor to move up. The e-box will then lower the chuck to bring that spot back down to where it should be. When we take the voltage off of the sample surface will go down, the laser spot on the photosensor will go down, and the e-box will then raise the chuck to bring the laser spot back to where it's supposed to be on the photosensor. In doing this, the chuck actually moves in the opposite direction of the surface of the sample, and the e-box keeps the cantilever fixed in space. The Z drive output is a voltage proportional to the voltage across the chuck, piezo element. So that means that its voltage is going to vary with the chuck voltage. It goes into the sensor input of the tester, so that if we run a hysteresis loop or a piezo loop or advanced piezo loop on vision, and it does a sine wave or a triangle wave across the sample surface will move. As it moves, the chuck will move up and down in the opposite direction of the sample surface. That voltage will show up here. The sensor input will capture that sample motion in exactly synchronously with the polarization hysteresis loop, and you will get two plots, the polarization plot and the butterfly loop. Now, because there's mechanical components involved in here, this type of measurement needs to be done very, very slowly, 1 hertz or slower, 1,000 millisecond period out to 30,000 millisecond period, to ensure that the chuck isn't vibrating and that it can follow the motion of the sample surface. Because the Z drive measurement is a slow measurement, any displacements measured with Z drive signal must be much larger than the ambient noise level. That can be from 150 angstroms up to several microns. To measure very small motions, we must get below the ambient noise level. To do that, we must go very fast. In that case, we use the Z error output. The Z error output is the direct output of the photosensor of the system. In this case, we run very fast, let's say a kilohertz. So the sample surface is moving much faster than the feedback system can move the chuck. In that case, the chuck stays stationary. The sample surface moves up and down. The laser spot moves up and down. That signal comes out of the Z error and is captured by sensor to give us the butterfly loop. If you have any questions, you can contact us at radiant@ferrodevices.com. You can also go to our PNDS webpage on our website at www.ferrodevices.com, and we will have a animated cartoon on that webpage showing the actual operation of the light lever and the chuck as the sample surface moves. Thank you.